Well, we've talked about terrestrial planets, we've talked about Jovian planets. We'll probably not have time to talk about the many wonderful moons in the solar system, but I hope you have the tools to go out and read about them and understand what the criteria are that one would apply to try to understand what they're like. But there are two types of object that I still want to mention. The first is asteroids. So asteroids are what we call planetesimals that, remember, never made it to planets. Most, but not all, also never melted and differentiated, and so they're still planetesimals. They never made it to protoplanet, and these are of great interest to astronomers because even the moon, our museum, was chemically differentiated, so the chemistry on its surface reflects chemistry billions of years ago, but not the chemistry of the original nebula, whereas some asteroids might preserve the actual intact chemistry of the solar nebula because their surface has not undergone differentiation. You will find exactly the traces of whatever it was that was around. So they're absolutely perfect museums, if you wish. Some of the rocks flying around in space may be the debris of late collisions, so do not reflect necessarily all of the early structure. There are many ways to generate rocks. Some never accreted. Some might be the result of collisions later. And some did melt, and those are called dwarf planets. A dwarf planet, for the record, is something that is in solar orbit, was big enough to melt and be in ellipsoid in hydrostatic equilibrium, but is not big enough to have cleared its orbit of everything else. This is the definition that caused poor Pluto to be demoted from actual planet to dwarf planet. The asteroid Ceres, as we'll see, is a dwarf planet. What do asteroids look like? Well, this is an image of asteroid PA8, a near-Earth asteroid. We see as it rotates, we see various sides of the asteroids. There's a chunk of rock. These are radar images. This is a near-Earth asteroid, but not a very close call. This one, at its closest, was 17 times the distance to the moon from Earth, but it was a good practice at taking pictures of an object as it approaches the Earth. These are Vesta, of which we saw beautiful images from the Dawn spacecraft previously, and Ceres, and we see that unlike Vesta, which is a planetesimal, Ceres is actually differentiated. It's a protoplanet. It's spherical. This is the largest of the asteroid, and it's the only object for now in the asteroid belt that qualifies for dwarf planet status, and we expect to learn much more about it when Dawn arrives at Ceres soon. So, various sizes of objects. Where do we find them? Well, most of them are found in the belt between 2 and 3.5 astronomical units away from the Sun, but as this image to the right shows, this is actually an image as of December 1st, 2012, I believe. Every green dot here is an individual asteroid. Every yellow dot is an individual asteroid. The red dots are also asteroids. These are asteroids that are in near-Earth orbit, that come close to the orbit of Earth. And as you can see, of course, their sizes do not reflect the actual sizes of the asteroids on this scale. They'd be much too small for us to see. But as you can see, there are many, many hundreds of thousands of objects that we have studied, and more are being discovered. I'll give you a link to the rate of discovery. There's a beautiful animation that makes this clear. And so most of them move, and then there are these gaps, Kirkwood gaps in the asteroid belt in which very little orbits, although there is the possibility of a stable resonance with Jupiter, and there are some asteroids that orbit in orbits that are resonant with Jupiter. These that we see in the first part of this animation orbit in a 2 to 3 resonance with Jupiter, so that they go around 3 times each time Jupiter goes around once. We've here frozen everything so that Jupiter appears stationary, so the picture is rotating together with Jupiter. We see the inner planets running around and Jupiter stationary, and we see these populations, and note that in addition to streaming from sort of one accumulation point to the other, periodically one of them, because of interactions with the rest of the swarm, gets shot down into the inner solar system. This collection are the Trojans. These orbit in a 1-to-1 resonance with Jupiter. You note they're not going anywhere. They're just orbiting these points 60 degrees west and east of the planet along its orbit. And again, once in a while, because of interactions with the swarm, one of these, or several, will shoot down into the inner solar system or be shot way out. And this is where near-Earth asteroids can come from. Now, when they get deflected and they come moving near Earth, they become meteors. When they hit our atmosphere, bits of rock in our atmosphere heat up due to friction. Most of them burn up. We see what we call shooting stars, which are meteors hitting the atmosphere. Some of them are large enough that even after burning, some survives to hit the ground. That makes them a meteorite. So a meteorite is a meteor that made it to the ground. Farther out, there are more objects. There are objects between the orbit of Jupiter and Neptune. Those are called centaurs. And beyond Neptune, we have trans-Neptunian objects. They include the Kuiper belt. Here's a display of known Kuiper belt objects, of which over 1,000 are known. They stretch out from beyond Neptune's orbit at 30 astronomical units all the way out to 50 and are strongly influenced by Neptune's gravity. That's what qualifies them, as one would expect from objects way out in the distant outer regions of the solar nebula. They're very rich in ices, so a lot of them is made of ice. These provide the source of short-term comets. Once in a while, gravitational interactions shoot one of these into the inner solar nebula, and because they're so icy rather than rocky, the big difference between a Kuiper belt object and an asteroid really is that an asteroid is made of rock and a Kuiper belt object is rich in ices, and the icy these form the source of comets, as we will see. The prevalence of short-period comets leads one to estimate that there are over 100,000 Kuiper belt objects with radii above 100 kilometers. So there are a lot of things out there. And then the long-period comets, as I said, predict this Oort cloud, which extends out to 50,000 astronomical units and is spherically symmetric. So the solar system goes on for a while. And investigating what happens to these things when they do get tipped into the solar system is sufficiently interesting that it's worth doing. So when something collisions or the perturbation due to Neptune slows one of these trans-Neptunian objects down into an eccentric orbit, taking them into the inner solar system, then they encounter, you have this ice ball, a dusty snowball is what they're called, with a radius of a few kilometers to 100 kilometers, say. And this now encounters the more intense solar radiation and the more intense solar wind in the interior of the solar system. And this is what creates a comet. This is what causes these objects to be both visible and sometimes, as the image nicely shows, very brilliant. The interaction with the solar nebula, with the solar radiation and the solar wind, creates a coma, the head of the comet, which is the brightest part we see. And then, as we can see nicely in this picture, two tails, a whitish curved dust tail and a straight blue glowing ion tail. And let's discuss what it takes to make a comet. So the nucleus of a comet, when it's visible, is hidden inside the coma. It's very hard to see. Only in the past few years have space missions been able to go and orbit the nuclei of comets far from the sun. This is Comet Tempel, and some of the things they found were somewhat surprising. This dirty snowball seems to have cratering in it, so it must be a more rigid thing than was imagined. In fact, somewhat brittle. So there's this picture that what we have is sort of an interlaced structure with ices and dust and ices and dust, ice serving as the glue. And what happens when this object approaches the sun is that the ices sublimate, they're heated, they turn to gas. At high pressure, they are ejected in jets carrying away dust. This is not a dust jet. This is the image of the Deep Impact. In fact, what the Deep Impact spacecraft did is it shot a projectile into Comet Tempel in order to generate a crater and study what the ejecta were to try to understand the inner structure of the comet. Studies of the results of this are still ongoing. But this comet is closer to the sun. We see the sun light hitting it from the right, and what we see is that on the side that the sun warms, we find jets emitted of these sublimated volatiles carrying away dust in jets, and this creates a tenuous, dusty atmosphere around the comet that, because the comet's gravity is very weak, this is an object a few tens of kilometers in radius, this dust sort of drifts around in a huge cloud that can be the size of the sun, and because it's so full of dust, reflects sunlight. And this is Comet Holmes, which in 2008 underwent presumably some kind of collapse of an ice cave or something, raising a big cloud of dust and generating a coma about the size of the sun that was visible to the naked eye as a blurry object. But this is why you cannot see the nucleus of a comet from Earth. Once a comet is visible, it's carrying around this huge tenuous atmosphere that is the coma. And then, besides that, there are two tails, and we saw the two of them. The image of a comet zooming across the sky with its tail strung out behind it is very natural and intuitive, but of course that intuition is based upon running around on Earth in the presence of an atmosphere. A comet does not zoom, a comet orbits. The orbital periods of comets range from a few decades to millions of years, and so their motion across the sky is very slow. They rise and set like stars, of course, and then they move across the celestial sphere at a rather dignified, slow pace. A comet and a shooting star are very different objects. Shooting stars, as I said, are terrestrial. We'll talk about that in a second. But they do sprout tails. These tails are the ejecta, gas and dust ejected from the planet, being pushed away from the sun by both the pressure of solar radiation. Light carries energy and also momentum, and light applies a pressure. And so the solar radiation as well as the solar wind push some of the ejecta out, stringing it out in a tail that can be a few astronomical units long. So astronomical unit, 150 million kilometers, the distance from Earth to Sun. These are solar system scale objects, these tails, that always point away from the sun, so that as a comet is approaching the sun, the tail stretches behind it. As it is moving away from the sun, the tail precedes it. This is not a problem. The two tails have to do with the two mechanisms. Dust, which is indeed propelled by the pressure of the sun, of both radiation and of the solar wind, is propelled away from the sun, but as the comet moves along its trajectory, the dust it ejected weeks ago remains pointed away from the sun at the position where the comet was, so it produces this magnificent arching structure. So here the sun is has just set, so it's below. The dust is being ejected in an upward direction, but the comet itself is moving from right to left, so that the dust it ejected a few days ago is now far to your right. On the other hand, the ion tail, the gases that are pushed away, and the dust tail is of course visible because dust reflects sunlight, so we see this beautiful white tail. The ion tail, not evident in this picture of Comet McNaught, but certainly evident in this picture, does not curve. It is always pointed directly straight away from the sun. The gases are ionized by solar wind, and then once you have charged particles, the interactions are governed by magnetic interactions, essentially. The comet acquires a magnetosphere. The magnetosphere interacts in a complicated way with the solar wind, and the result is that the ion tail always points directly away from the sun and is redirected, if you will, as the comet moves, so it does not curve. And ionized gas recombination, the same kind of ghostly blue glow that we saw in our electron tube, is how you characterize the ion tail. So these are these beautiful objects, comets. But a comet can't last forever. It's an ice ball. As the ice evaporates, remember, ice was perhaps the glue that held things together, and a comet can't last forever. How do comets end? Well, one of four possible ends, I guess. One is, these things are in highly eccentric elliptic orbits. They can come close to the wrong object, Jupiter, Neptune, Uranus, and collide gravitationally in such a way that they're completely ejected from the solar system. This certainly can happen, especially to the Oort cloud comets that are rather weakly bound, so a small perturbation can send them completely out of the solar system, and then they won't come back. Another possible end is extinction. Eventually, a comet might run out of volatiles, have them all sublimated away, or maybe some of them might be sealed deep inside the comet but inaccessible, and so you have basically a chunk of rock now, or dust, orbiting the sun. It'll never make a comet anymore. Some suggestions are that as the ice leaves, the thing compacts, and maybe some of what we call asteroids are essentially extinct comets, having been deprived of their volatiles after passage through the sun. Another possibility is disintegration. You lose the icy glue that held together the dust, either the recoil from these jets emitted on the sun side or the tidal forces of the sun or some planet near which you come can cause a comet to disintegrate, as in these Hubble images brilliantly, Comet 73P, the P, by the way, stands for periodic, is shown disintegrating, and then the bottom image shows from the ground, shows that there are many more fragments scattered around, so there's a hierarchical fragmentation going on. And then the other possible end for a comet is a collision. Famously, in 1994, Comet Shoemaker-Levy 9 did both. It first disintegrated into about 19 pieces in the tidal force of Jupiter, which it was approaching, and then sequentially, one after the other, all of these plowed into Jupiter, giving us a rare and at the time unique opportunity, perhaps to see what ejecta they pulled out of the atmosphere, and to learn something about the constitution of Jupiter's atmosphere. Sadly, this collision occurred on the far side of Jupiter, so we couldn't see it, but every telescope on Earth was trained on Jupiter because Jupiter rotates so rapidly that within 20 minutes after the collision, the impacted areas face the Earth, and in this Hubble telescope image, we see at least 4 of these dark spots in the lower right-hand corner of the planet, which are collision zones where fragments of the comet collided with Jupiter. This was so successful that a decade or so later, we dropped a probe of our own into Jupiter's atmosphere to try to understand the constitution and processes inside Jupiter's atmosphere, with mixed results, I should say. And if a comet does not collide with a planet like Jupiter, then of course there's always the option of collision with the Sun. Here we see Comet Lovejoy plowing on its way to the Sun. We see the magnetic interactions between the solar wind and the tail cause all this complicated dynamics in the tail. The comet is on its way to a fiery death. We see the comets diving into the Sun with reasonable regularity. The exciting thing about Comet Lovejoy is that it actually survived the encounter and came out the other end, and so a year ago there was great joy among the sun-grazing comet community when Lovejoy actually survived the collision. You can look it up and find the breathless blogs. So comets don't last forever, but they leave a trace. So every time a comet comes near the Sun, a bunch of it evaporates. It leaves behind this dust and gas that it ejected. All of this dust is scattered about the comet's orbit, and as we discussed, what that does is the bits that are too close to the Sun in inner orbits get stretched out ahead of the comet. Bits that are a little bit behind, outside the orbit, become stretched out behind the comet, and essentially this dust forms a ring-like structure around the entire orbit of the comet. And after a few passes, the entire orbit of the comet is full of this orbiting space junk, debris from prior passes near the Sun. And what this means is that if a comet's orbit happens to intersect or come close to the Earth's orbit, then, well, the timing is off. We might not collide with the comet, but once a year, when the Earth approaches that point in its orbit at which it is crossing the trajectory, the orbit of a comet, then we will experience an increased incidence of space junk. We call that a meteor shower, and it's a predictable event because we know where the comet's orbit is. Not only will the incidence of space junk and shooting stars be increased, but because they are all orbiting in some particular orbit of a particular comet, the Earth is moving in a particular direction, there will be a predictable, repeatable direction from which all these shooting stars will appear to come, because they all impinge the Earth, moving in roughly the same relative direction. In this beautiful image from the 2001 Leonid meteor shower in November 2001, which was particularly brilliant, what we see is that indeed there are shooting stars all over the sky. These meteors hit the atmosphere where they hit it, but they all appear to be coming from one point in the sky. This is called the radiant. In this case, the radiant for the Leonid shower is in the constellation Leo. They all appear to be coming from there. If you look at this, you immediately see the perspective point of view. This is the direction from which all of these space debris is impinging upon the Earth, and this is the source of our annually repeating periodic meteor showers.